All right, guys, let's talk about section 2, how the materials get cycled around. Section 1 was how energy gets cycled. All right, when we talk about food chains and food webs and how the energy moves. Now we're going to talk about like nutrients, uh, carbon, nitrogen, potassium. We're talking about how nutrients and materials get transferred around. Okay, so we did energy first, and now we're doing nutrients. Let's see. So we're going to list the 3 stages of the carbon cycle. Okay, we're going to describe where the fossil fuels are located. We're going to show ways that the humans are affecting the carbon cycle. Then we're going to list 3 stages of the nitrogen. The role that nitrogen fixing bacteria, that's going to be really important, nitrogen fixing bacteria play in the nitrogen cycle. And then we're going to show how excess use of fertilizer can affect both nitrogen and phosphorus cycles. All right, so starting with carbon. The carbon cycle is the movement of carbon from the non-living environment. You know, remember we learned about biotic and abiotic? We learned about biotic and abiotic. Okay, so carbon by itself is abiotic. Carbon by itself is not a living thing, but all living things need it. So we've got to get carbon from the non-living environment into living things and back again. So it's essential for proteins and fats and carbohydrates. It's one of the most important ingredients in a living thing. They, in fact, so much if you watch sci-fi, they call us a carbon-based life form. Okay, that's what they call all living things on Earth, whether they're talking about trees or animals or people or even bugs. Okay, they call us carbon-based life forms. Carbon is that important. Okay, it makes up all the proteins, the fats, the carbohydrates, makes us all up. The carbon cycle is a process by which the carbon is cycled between the atmosphere and the land and the water and the organisms. Okay, so between the atmosphere, okay, the land, the water, and the organisms. And look, not just living things. Okay, everything needs carbon. All right, so here's the basics, and I don't think there's another click on this slide. I don't know, we'll see. Okay, so we have remember we're learning about fossil fuels, natural gas and oil. Both of those are full of carbon. Okay, you have erosion wearing down the soils. Carbon dioxide gets dissolved in the water. Okay, then here's some more natural gas and coal. Okay, we use it to light our houses and burn our fuels. Okay, then it goes out into the atmosphere as, again, carbon dioxide. The plants take that carbon dioxide in. All living things breathe out carbon dioxide. And look, this says decomposition. When something dies, it breaks down to the soil. It adds the carbon. Okay, this is respiration. This is breathing it in and breathing out carbon dioxide, and photosynthesis taking in carbon dioxide. Those are one of the primary spinners. Respiration and carbon dioxide. I'm sorry, respiration and photosynthesis, which we learned 2 sections ago. No, at the beginning of last section, we focused really hard on photosynthesis and respiration. Okay, and those are the key drivers of the carbon cycle. So again, the short-term cycle, the easy one, is what I just said right here. Okay, we breathe in carbon dioxide. We breathe out carbon dioxide. Okay, and the plants breathe it in. Okay, and give us back oxygen. Okay, then we breathe out carbon dioxide, and the plants take it in and give us oxygen. So carbon exists in the air, in the water, and in living things. The short-term cycle is where the producers, the plants, are going to convert carbon dioxide in the atmosphere into carbohydrates during photosynthesis. If you remember the first ingredient in the glucose molecule, do you remember learning what glucose, the formula? C6H12O6, that's C. In glucose, C6H12O6. That's the carbon, all right? So the plants take in carbon dioxide, and then they attach that non-living abiotic carbon dioxide onto their glucose molecule, which is an organic thing, a living biotic thing. Not living, but it is a biotic material. So consumers can obtain carbon from the carbohydrates in the producers that they eat. And then during cellular respiration, the carbon dioxide is released back into the atmosphere as we breathe out. The long-term cycle, okay, so that was a short-term cycle, you know. We breathe it out, the plants take it, and they give us the oxygen, okay, or we eat it in the glucose, either one, okay. Those are both part of the short-term cycles. The long-term cycle, though, okay, the carbon can be converted into carbonates, which is bones and shells. Okay, and so the bones and shells obviously don't break down very easily, and so over millions and millions of years, these carbonate deposits are going to produce huge formations in limestone rock. This is, ancient shells of an ocean creature. That's what these rocks are. Okay, so limestone is one of the largest carbon sinks or carbon storage reservoirs on Earth. So there is a lot of carbon tied up in the rocks. Okay, that's why the carbon sink means just a place to store it. Storage. That's what a carbon sink is. Or if they say a nitrogen sink or whatever sink, okay, they're not talking your kitchen sink usually. They're talking storage area. Alrighty, so again, as one way that you can store a bunch of carbon is with the limestone rocks, but you can also store a bunch of carbon as the fossil fuels. Okay, a bunch of carbon is stored within the fossil fuels. So carbon is stored in the bodies of organisms like fats, oils, or other molecules, and can be released into the soil or air when that organism dies, whether it's a plant, because there's oils in plants, or an animal. Okay, when that organism dies, some of those fats, oils, and other stuff that are full of carbon get released into the soil. And as they do, they can become coal, oil, or natural gas, fossil fuels. That's dead organisms, the carbon that used to be in dead organisms. So the fossil fuels are stored carbon left over from the bodies of plants and animals that died millions of years ago. So that's another place to store carbon. So you can store carbon in limestone rocks when it comes from bones and shells. You can store carbon in fossil fuels when it comes from fats and oils. Both of them happened, something died and they just left their left their remains behind. And so limestone rocks is a good carbon sink made from bones and shells. Fossil fuels, another good carbon sink, all right, that's used from the oils and fats in the organisms as they die. And the trouble is we need to leave it in there. We need to leave it in the carbon sink. We don't need to be releasing it back into the atmosphere because we have plenty already in the atmosphere. So how humans affect the carbon cycle, this is what we're talking about. All right. All right, so humans burn the fossil fuels, releasing carbon dioxide into the atmosphere, and then it turns, releasing the carbon into the atmosphere, and it turns into carbon dioxide. So cars, factories, and power plants, they're the source of 1/3 of all the carbon dioxide emitted from the United States. So when we take these fossil fuels, remember, fossil fuels are a carbon sink that's made from the oils and fats of ancient organisms. When we burn fossil fuels, we release that carbon back into the atmosphere, okay, as carbon dioxide. And then, of course, the carbon dioxide is what's heating up the world, okay. Over a period of years, the amount of carbon dioxide in the atmosphere has steadily increased, and along with it, global warming has occurred because this carbon dioxide that's coming out from the factories and from us burning the fossil fuels is heating up the world. These increased levels of carbon dioxide contribute to global warming, and global warming is officially an increase in the temperature of the Earth. Global warming and the greenhouse effect are not 100% the same thing. The greenhouse effect, remember how we said that you have the heat trapping inside of the atmosphere? Okay. The greenhouse effect will cause global warming. Okay, global warming is just the increase of temperature of the Earth. And it's been melting the glaciers and heating the oceans. Okay, you see our poor polar bear right here? They are very close to extinction, okay, because they swim really well, but they can't hunt while they're swimming. And they need the camouflage of the ice. If they're trying to hunt on land and it's like bushes and trees and mud and dirt and stuff, they're going to stand out like a sore thumb. They're not going to be able to catch their food. All right, so the melting glaciers is causing the extinction of the polar bears and several other of the Arctic species. This video here is amazing. All right, if you can take a few minutes to watch it, it's really, really good. I don't know if I'm going to assign it for film facts or not, but it's a very good video. It helps to explain a lot about the carbon cycle. All right, moving on to the nitrogen cycle. The nitrogen cycle is a process by which nitrogen circulates among the air, soil, water, plants, and animals in the ecosystem. So we just finished carbon cycle. Now we're doing nitrogen cycle. Okay, all of the organisms need nitrogen, okay, for DNA and to build their proteins. And nitrogen makes up 78% of the gas in the atmosphere. All right, so think about why nitrogen is important. Okay, plants need it for chlorophyll. Remember, that's the key that lets them do photosynthesis. We don't have any chlorophyll, right? Chlorophyll is the stuff that make plants green, and they need that in order to do photosynthesis, and nitrogen is an important component. You remember how DNA is made, okay? Every step on this ladder, okay, on both sides of the ladder requires nitrogen. So you have nitrogen on both sides of every single step. Every rung of the ladder needs nitrogen. And if you remember, DNA is a huge molecule, and we have trillions and trillions of cells in our body. All right, and if every single rung of the ladder needs nitrogen, that's a lot of nitrogen you need to make for your DNA. All right, so it's really important. And then when we are taking our DNA and then creating proteins and amino acids, those are also requiring nitrogen. And so here's what we're beginning right here. 78% of the atmosphere is nitrogen. Sounds like a good thing, right? We can't use atmospheric nitrogen. Oh, my picture's in the way. We cannot use atmospheric nitrogen. You can read that behind the picture, right? You can see the word atmospheric right here. Okay. We cannot use atmospheric nitrogen. What that means is, yes, 78% of the atmosphere is full of nitrogen, but when we breathe in, the nitrogen comes in and it goes right back out again. It comes in and it goes right back out again. We can't use air nitrogen. We have to have solid nitrogen in order to be able to use it, and we need a lot of it. Plants need it for chlorophyll, we need it for DNA, we need it for protein, we need it for a lot of the chemical processes that are happening in our brains and in our muscles. We need it for that too. All right, so nitrogen is crazy important, but every time we breathe it in, it goes right back out. Useless. Even though 78% of the atmosphere is nitrogen, completely useless. All right, well, how do we get it then? All right, that's what we're covering next. How do we get it? Atmospheric nitrogen is no good. We need solid nitrogen, okay? The nitrogen has to be fixed so that we can use it. All right. Let me see if there's another click. Yeah. All right, so the nitrogen has to be altered or fixed before we can use it. We can't use atmospheric nitrogen. We have to use solid nitrogen. And only a couple of species of bacteria can fix this for us. Okay, it's bacteria that fix the nitrogen for us. They're going to fix it and turn it into chemical compounds that we can actually use. All right, now this is what I mean by fixing it. Atmospheric nitrogen is no good. There's these bacteria that can fix it for us. They basically turn it solid. Okay, these bacteria are called nitrogen fixing bacteria, and it's only a couple of species. Not every bacteria can do this. Okay, all other organisms depend on these guys to give us our nitrogen. All right, and we're going to talk about where they live, okay, and how they get the nitrogen for us. I think that's on the next slide. All right. One more click. Yes. Okay. Yeah. This is where they live. All right. So the nitrogen fixing bacteria can convert the atmospheric nitrogen into ammonia compounds. Okay. So they take the atmospheric nitrogen and turn it solid. These bacteria live within nodules on the roots of plants called legumes. Okay. Now let's work this out. Okay. The plant itself is called a legume. Okay. That's like peas and beans and peanuts. Okay. And clover. Okay, so not every plant, but special plants called legumes. That's the type of plant it is. All right, and they live in nodules on the roots. So these bacteria live in nodules on the roots of legumes. Legume is a type of plant. And do you see these nodules? They're like the little houses or apartment buildings. Okay, these bumps. Okay, these are the little apartment buildings for those bacteria. So they live in these nodules on the roots of legumes. Okay, and then the bacteria are going to use the sugar that's provided by the legumes. Remember the glucose when they do photosynthesis? Okay, so the bacteria eat the sugar, and when they do, they make these nitrogen containing components called ammonia or nitrates. So they take the sugar that the legume has made, and when they process the sugar and when they eat it and digest it, they make ammonia and nitrates. And then the plant is going to use these ammonia and nitrates to build its own DNA. All right, because plants need DNA too. And so then when something eats that plant, they get the DNA full of nitrates and nitrogen, and then they can use it. So, and also the nitrogen-fixing bacteria are going to make some extras. The plant's going to take as much as he needs to make his DNA, but then there's extras. So the extra is released into the soil, and then other plants can use it, like grass and stuff that's not a legume. All right, the plain plants can use it now once it hits the soil. So in addition, some of the nitrogen-fixing bacteria already live in the soil rather than inside the roots. So that's a bonus, okay? And plants that don't have the nitrogen-fixing bacteria can get it from the soil. And then once the plants have it, then of course the animals can get it by eating them. All right, so the nitrogen-fixing bacteria are a crucial part of the process in which the nitrogen cycles between the atmosphere and bacteria and other organisms. All right, so here's our plant. This is a special plant called a what? What do we call this kind of plant? A legume. And the bacteria live in nodules on the roots of the legume. Okay, they're going to fix the nitrogen. Okay, and so once they take the sugar that the plants have made, they process the sugar, and then they're going to release nitrates. The plant can use it, so anything that eats the plant now can get hold of it. They will put their extra out in the soil. If they make extra nitrates, it goes in the soil, and then the next plant that grows out of the soil can use it, and then something can eat that. Okay, and then the bacteria don't live very long, so when they die, their bodies are full of nitrates. That's going to get put in the soil. The plant that was able to get the nitrate, when it dies, it's going to go to the soil. Okay, so now we've turned all this atmospheric nitrogen into something solid because of these one little bacteria. All right, and so then we go on. All right, so here is our nitrogen cycle. This one's in their text. All right, so here's the legume and the nitrogen-fixing bacteria in the soil. Once they die, it gets into the ground, and then other plants can use it, okay? And then anything that eats any of these plants can get it by eating it. Now, here's the cool thing. There is a bonus. Can you see that this is lightning over here? One cool thing about the nitrogen cycle, okay, is that lightning, remember we said the air is like 78% nitrogen. Okay, I'm going to talk, there's parts of notes about this in just a second. I just want to show you the picture. The air is 78% nitrogen. Lightning strikes are 5 times the heat of the sun. When lightning strikes, it fries the air. And then all that atmospheric nitrogen, it just got fried. The ash of the nitrogen goes down into the soil. Let me show you. It's in our notes. Go ahead. Here's the notes. Lightning and the nitrogen cycle. So in addition to the nitrogen-fixing bacteria, atmospheric nitrogen can be added to the cycle through the action of lightning. Lightning can heat the air as it passes through to 50,000 degrees Fahrenheit. Okay, that's crazy hot. Lightning strikes 50,000 degrees Fahrenheit. I had to look this up myself. It's accurate. Okay, it's 5 times hotter than the sun. This in effect fries the nitrogen in the air, and then that solid ash falls to the ground, and then that can be used as well. So you have these nitrogen-fixing bacteria that are working in the soil. When this plant dies, or when the bacteria in the soil die, they're going to put it in the ground. All right. Then the other grasses and plants can use it. Then there's actually some bacteria that just live in the ground, okay, taking nitrogen from the air, okay, and turning it solid so that everybody else can use it. When something dies or goes poo, the nitrogen gets put back in the soil. All right, and then it's used and used and used and used and used. And then we also have the action of lightning that will fry some of the nitrogen that's in the air, and then the ash drops down to the earth, and then that can be used by the plants. And then of course something eats that and something eats that. All right, now the decomposers and the nitrogen cycle, like I said, something dies, we can use it. Okay, the decomposers help us do this. The nitrogen stored within the bodies of living things, plants or animals, is returned to the nitrogen cycle once those organisms die. The decomposers are going to break down the decaying plants and the animals, as well as the animal waste, because there's a lot of nitrogen in pee especially. Okay, so after the decomposers return nitrogen to the soil, the bacteria transform the small amount of nitrogen back to nitrogen gas, so that some of it goes back out into nitrogen in the air. Okay, once the decomposers work on it, some of it stays solid to be used the next generation, but they call this denitrifying bacteria. that put it back into the air so that the cycle can continue, because otherwise over time there'd be less and less nitrogen in the air, wouldn't there? Think about how old the Earth is. The Earth is almost 5 billion years old. Over time, if we had the nitrifying bacteria, the nitrogen fixing bacteria, eventually there'd be no atmospheric nitrogen left. So there are these denitrifying bacteria that put it back as a gas again, so that the cycle can keep going. All right, so once the nitrogen enters an ecosystem, most of it stays within the ecosystem. Most of it, once it turns solid, most of it stays solid. But then again, there are the ones who put it back as gas. So the cycles between the organism and soil is constantly being reused. Okay, Earth's recycling system. All right, so here we go, this nitrogen. See these NO2s? That N is for the nitrogen, okay? So we have this, yeah, this is basically what we're talking about. The animal, when it dies, see the bones, or the animal's poo, okay? All right, so we got that. I think you've got it. But anyway, what this slide is a video. Like I said, I found another great video to show you the nitrogen cycle. So you had a great video for the carbon cycle and a great video for the nitrogen cycle. I would love it if you watch them. That way you're sure that you understand it really well. These cycles are a huge part of your biology class. Most of you are taking biology next year. Not everybody, but most of you. These cycles are a big, big thing for your biology class. And the more you understand now, the better you'll be. Phosphorus cycle is next. I don't think there's a picture on this one. Okay, so the phosphorus cycle. Phosphorus is an element that is part of many molecules that make up the cells of living things. Bones and teeth, muscles, and the chemicals in your body that makes your brain and your muscles work. Really important for those. So it's important for the chemicals also. So plants are going to get the phosphorus they need from the soil and the water, while animals get the phosphorus from eating the plants or other animals that have eaten the plants. So that part of the cycle is normal. The plants get it out of the soil, and then something eats that, and something eats that. And the phosphorus cycle, officially, the official definition, the cyclic movement of phosphorus in different chemical forms from the environment to organisms and back again to the environment. The thing that makes the phosphorus cycle different than the other two, like I said, we've covered carbon first, and then nitrogen, now phosphorus. The thing that makes phosphorus different is that there's no phosphorus in the air. There's no atmospheric component. That's what you say. There's no atmospheric component to phosphorus. Okay? It's not in the air at all. The only way you get it, it's in the rocks. Okay, it starts off in the rocks, and then erosion is going to bring it down to the soil. Okay, and once it's in the soil, the plants can use it. Okay, or it goes in the water, and the water, the phosphate kind of builds up and it sinks down into the water. Okay, until it becomes rocks again. Okay, and then we use a lot of phosphates for fertilizer. We use phosphates and nitrogen. I'm going to talk about those in just a second. Phosphates and nitrogen, because the plants love them so much, we use them for fertilizer a lot. All right. So then we have, of course, we have the decomposition of plants and animals. It's going to put phosphate back in the soil, and then the plants are going to take it up again. It's going to erode down from the mountainsides in the water, and then it'll build up in the water until it makes rocks again. But that never, ever once does it hit the air. Phosphorus does not hit the atmosphere. Okay, so it rarely occurs as a gas, and therefore it has no atmospheric component. And since we have to rely basically on the rock cycle, right? You have rocks, and the rain erodes them. They turn back into rocks. Remember how slow the rock cycle is? You learned it back in middle school, remember? The rock cycle is crazy slow. And the phosphorus is tied to the rock cycle. So it is a really, really slow process. And what we're going to cover in just a second, because it's so slow, okay, it's called a limiting factor. The plants really, really need to have it. The animals really, really need to have it. Okay, we can only have as many plants and animals as there's enough phosphorus to go around. Think about it. It's called a limiting factor. Everybody needs phosphorus. Okay. And everybody needs nitrogen. Okay, and every single plant, every single animal has to have phosphorus, has to have nitrogen. They're called limiting factors because we can only have as much plants and as enough animal as there's enough phosphorus to go around. Okay, so it moves from the deposits in the rocks, it moves then to the land and the soil through erosion, and then back into the living organisms and finally to the ocean. So it's very, very slow. Very, very slow. And so it also limits the number of organisms that can be in an ecosystem. The phosphorus can enter the soil and the water when the rocks erode. Small amounts of phosphorus is going to dissolve into phosphate, which moves into the soil, and that's not real important. But the plants can absorb these phosphates that are in the soil up through their roots. Then the consumers are going to ingest them, and then they're going to excrete them in their wastes. So once the consumers have eaten the phosphates that are part of the plants, they're going to excrete it in the waste and then return it to the soil when they die. Some of the phosphorus is going to wash off the land through the erosion, and it's going to end up in the ocean. And many of the phosphate salts are not soluble in water. Okay. Remember I said we started off with phosphorus and we turned into phosphate. That means we did a chemical reaction on it. And a lot of these chemical reactions are not water soluble, so they don't dissolve in water. And once that happens, though, they're going to sink down to the bottoms of the water, whether it's ocean or rivers or whichever it is, saltwater, freshwater, it doesn't matter. They're going to sink down to the bottom of the water, and then they accumulate as sediment and become rocks again. Okay, so you kind of remember how the rock cycle works. All right, so we have phosphate eroding off the rocks. We have phosphates in dead animals. Okay, and then we have the rain washing this phosphates down into the waters usually. Because it's not soluble in water, the phosphates are going to accumulate down on the bottom and turn back into rocks and again. But once we have the erosion going on through here, the plants are going to take some of it. It's going to be part of the plants, and then of course part of all plants, and then the consumers are going to eat them, whether it's us or the animals. And then it's going to be excreted back down with the waste of the animal or when the animal dies. And again, this guy is digging out phosphorus on purpose because phosphorus is an important limiting factor, right? Every single organism on Earth needs phosphorus, and we can only have as much plants and animals as we have enough phosphorus to go around, so we use it in our fertilizer. Okay, so that's why we're getting the phosphorus and the nitrogen. And here's the third video. Remember I said I have a great video for each one of the cycles. Each one of the cycles, these videos explain it really, really well. All right, now, again, fertilizers and the nitrogen and phosphorus cycle. Is there one more click? Yes, okay. All right, so, as I said, because nitrogen is in the air we can't use. We can only use solid nitrogen, and we have to rely on those bacteria to make it for us, nitrogen. And then phosphorus, we have to wait on the rock cycle. That's even slower than the bacteria. So both nitrogen and phosphorus are limiting factors. We can only have as much plants and animals as we have enough nitrogen and phosphorus to go around. So we decided to start making fertilizers. All right, so that makes sense. However, humans, once we made fertilizers, we say, a little bit is good, but a lot's going to be great, right? We need even more plants. All right, they'll grow even bigger. The plants will be bushier. We'll get more fruit and more stuff off our plants. So put more fertilizer and more fertilizer and more fertilizer. Well, that gives us a problem. Okay, so the fertilizers that the people use to stimulate plant growth contain both nitrogen and phosphorus. Okay, that's obvious. But we use too much. It works really good, so we use too much. Okay, the excess fertilizer can enter terrestrial and aquatic ecosystems through runoff. Okay, so we fertilize the grass up here, all right, and the farms or whatever, and then the runoff brings that extra fertilizer into the creeks and the streams and the rivers and the oceans. All right, and it causes this rapid growth of algae. Okay, algae's a plant, sort of. It's a protist. It loves all this fertilizer that we're adding to the water. Well, theoretically, it's called an algae bloom. Okay, when we added too much fertilizer, and now all of a sudden there's algae all over the top of the pond. It's called an algal bloom. That's the easy one to remember. You bloom. It's a plant. An algal bloom. Okay, the fancy word for algal bloom is this, eutrophication. Eutrophication is the fancy word for algal bloom. Too much algae is called eutrophication. You'll need to know this word. Okay, so eutrophication or algae bloom is a dense, visible patch of algae that grows near the surface of the water. Okay, well now, we would think, all right, that that might be a good thing, right? Turtles love this stuff. The animals love this stuff. They can eat this stuff. Well, they can't eat it fast enough. They can't eat it fast enough. And so what winds up happening is that this algae is going to cover over the top of the pond. All right. There are bigger, more established plants down here at the bottom of the pond trying to grow. The algae blocks off the sunlight, so these plants start to die. Remember that while the plants are living, they're going to create oxygen for us. When they die, the decomposers, because the decomposers are actually eating the dead stuff, they're going to put out carbon dioxide. Just like when you eat your food, you put out carbon dioxide. That's cellular respiration. You eat your food, you digest it, you try to use it, and you put off carbon dioxide as a process. Well, when the decomposers are eating these dead plants, they're going to put off carbon dioxide. So the plant dies because the algae is blocking the sun. The plant dies, so it's not putting out oxygen anymore. And the decomposer is eating up the plant and putting out more carbon dioxide. So the oxygen is almost gone out of the water. Try to think it with me. There's no oxygen in the water left. I'm not just talking bubbles. The oxygen is actually dissolved in the water. The fish pull it in through their gills. Okay, it's not bubbles. It's actually dissolved in the water. That's what the fish are breathing through their gills. So the algae blocks the sunlight. The deeper plants that are in there die, so they're not making oxygen. The decomposers are eating them, so they're putting out even more carbon dioxide. The oxygen doesn't get replaced, and now the fish are suffocating. There's no oxygen for the fish. The plants are dead down there. There's no oxygen being made, and so the fish start to die. And then the decomposers eat them, and they're putting out even more carbon dioxide. Do you see how it's a snowball effect happening? The oxygen is completely starved out of the water, and everybody just suffocates. Everything that lives in there that can't get up for air. I mean, the turtles can still live there. They can come out to breathe. Fish and stuff, they're going to die. As they die, their bodies decompose, which adds even more carbon dioxide to the water, which heats up the temperature. The carbon dioxide makes it hotter. So this excess algae is going to deplete or use up the important nutrients like the oxygen on which fish and other aquatic organisms depend. All right, now the next thing that happens is acid rain. That's another thing that the humans do that are messing up the cycles. This one is mostly for nitrogen. Okay, when fuel such as coal, oil, or wood is burned, large amounts of nitric acid is released in the atmosphere. Nitric acid, so this is part of the nitrogen cycle. Nitric oxide is a harmful gas, and when it's released into the air, it can combine with oxygen and water vapor to form nitric acid. And this nitric acid can dissolve inside the rain and snow and fall as acid rain. So this is coming out of the smokestacks and stuff when we burn coal, oil, or wood. Okay, comes out of the smokestacks. It mixes with the rain and comes down as acid rain. And that acid rain can actually start dissolving things like it can even dissolve statues. There are beautiful statues. You know, think about ancient Greece and ancient Rome, all those places that had made all those statues everywhere. Once humans became industrialized and started burning all these coals, these statues that had lived for thousands and thousands, had stood for thousands and thousands of generations to mark these ancient ruins and these ancient temples and stuff, they had stood there through time until humans became industrialized and we started burning coal and stuff, and now the statues are disintegrating. Okay, now we have made a good amount of progress in what we're doing to take care of acid rain. This is one of our happy stories. Usually when I'm talking about humans and the environment, they're sad stories. Oh no, we're using up all the oxygen, we're putting too much carbon dioxide in the air, and we're melting the glaciers, and usually it's bad news all the time. Okay, this is one thing we've just about fixed. Okay, so this is another good video for you, all right, to help you understand the material in the chapter. All right, so here's our main ideas that we've covered today. Okay, the materials in the ecosystem are recycled and reused by natural processes. Carbon, nitrogen, and phosphorus are all essential for life, and each one of them follows a recognizable cycle. Humans can affect the cycling of material in the ecosystem through activities like burning fossil fuels and applying fertilizer to the soil. Those are the main things we do, all right, that affect the cycles. All right, so I'm pretty sure you've got this. Okay, you might want to watch the video a second time just to be sure, but we've been doing a lot of work on the chapter, so I'm hoping you're good. And study well for the test, and I'll see you guys the next time.